Hi, my name is David Bradwell, and I'm the Chief Technology Officer, Co-Founder, and Senior Vice President here at Ambri. I'm happy to provide you with a tour of our facility out in Marlborough, Massachusetts, where we do our cell development work, systems development work, and prototype manufacturing. I'd like to start the tour by walking you through this area over here, where we have a little demo space where we can talk through a bit of a background on our technology, as well as our materials flow and facility layout. So here we'll walk through this little demo area here. First thing we want to point out is how the cell operates. This is an image that depicts the operation of the cell chemistry. You can see here that the cells are loaded with calcium and antimony metal as the two electrodes, and then a molten salt electrolyte containing calcium chloride. The cells operate at an elevated temperature such that the molten salt is in a liquid state, calcium is in a liquid alloy, and then this antimony is actually stays as a solid particle mixture with salt surrounding it. And so the three components here you can see include this calcium, which is received like this, calcium chloride based salt, which is effectively road salt, and antimony, a commodity commonly available material, which is our positive electrode. So these components get loaded into a cell, and then during the operation, the calcium sheds electrons, passes through the electrolyte as an ion, allowing electrons to go through an external circuit, which recombines with the antimony and calcium ion to form a calcium antimony alloy. During charging, the exact reverse process happens, and electrons are pumped from the positive electrode to the negative electrode, pulling calcium ions from one electrode to the other, allowing it to redeposit. So during this operation, the calcium is consumed on discharge and then redeposited and created on charge. And that's one of the reasons the cell technology can operate for thousands and thousands of cycles with minimal degradation. So these components are loaded into cells. Here's an example of an R&D cell. You can see this lid here is removed during assembly. The calcium and antimony are loaded into this cathode bay. Molten salt is poured into the cell, and then this cap is loaded back on and welded shut. And then to charge the battery, electrons are pushed through, or current is pushed through the negative current lead rod here and extracted out of the body of the cell, which is case positive. And the cell is subsequently charged up, and the calcium deposits into this porous current collector. So you can see during an assembled state of the cell, in a charged state, the calcium is in negative electrode here, antimony is in the positive electrode compartments here and here, and the battery is then ready to discharge. One of our big focus right now is on scaling up to large commercial cells. This is an example of a large commercial cell that is being developed presently and going through verification testing. And ultimately, we're going to take cells like this and string them together into a system like this, where individual cells are strung onto trays, loaded into a frame, and a rack system. That frame is loaded into a container, like a 10-foot shipping container unit, and then we fill the space between the frame and the container walls with thermal insulation, and the cells are heated up, and once they start operating, they generate some of their own heat through the inefficiencies of charging and discharging, and that allows them to the system to become self-heated. So now that we've walked through some of our demos here on this display counter, I want to show you a couple other cells that give a better idea of what the cell actually looks like on the inside. And so these components I'm bringing out here are from an older version of a cell design that we initially pursued, which was taller than the cell design that we're pursuing presently, as you can see, but it still has a similar internal design and features. So this component here, this is the negative current collector. This is a porous metal structure into which the calcium liquid alloy wicks and wets into. Similar to water soaking into a sponge, the liquid calcium alloy wets into a metal structure like this, allowing to hold it in place during the operation of the cell. It's really quite an innovative kind of design element to our cells. And that negative current collector is placed inside of the cells, as you can see here. And then to the left and the right of this bay are cathode bays. This is where the antimony particles are located during the operation of the cell. So this is all kind of put together here. Obviously there's a cap that goes on top, which isn't shown. But the result of it is a cell that kind of looks like this. And if we cross-section it, and this is just for demo purposes, but you get a sense of what it looks like on the inside of the cell. So the cell has this negative current collector down the center, and then the antimony particles are located in the two bays on either side. And so that's really the internal configuration of the components, with the antimony, the salt, and then the calcium wets onto the negative current collector, current lead rod in the center of the cell. I also want to share with you here one of the cell positive current collector assemblies that we've received from our one of our vendors that we're really excited about. This is a cell assembly with 4 cathode bays into which we'll load a negative current cap that'll have 3 center plates here for the negative current collector. And the cell is assembled with the calcium and antimony loaded into each of these bays, filled with salt, and then welded shut. So we're really happy to see this. So this is one of the cell components and assemblies that we're going to use as we scale over the 2021 timeframe. So now that we've talked through some of the background on the technology, I'll give you an overview of our facility here and then provide you with a tour. So up here we have some posters that describe the materials flow and the facility layout. We're going to start with talking about the materials flow. It all starts with incoming, shipping and receiving, quality inspection, parts cleaning and salt conditioning. So getting the parts all ready to go to be used in building cells. Those parts then go into inventory, either into our commercial cell warehouse, seal warehouse, or R&D cell warehouse. We then fabricate the components, including fabrication of the seal technology, as well as the R&D and commercial cells. Assemble those components into cells, filling them with the molten salt and the active calcium and antimony metals. And then once assembled, the cells go into testing, and under end-of-line testing to ensure quality and also for development purposes. Cells, once they complete their testing, they'll either go be sectioned and analyzed and go into disposal and recycling, or they get packed up and shipped into containerized systems. So this is our overall facility, which maps against the process flow as described earlier. So we start off here in the shipping and receiving space. So we are in this location here. Shipping and receiving is behind us. We have some cell warehouse space, some salt conditioning area, quality inspection for the parts as they come in, and parts cleaning. The parts are then brought over to our cell fabrication area where we build our commercial cells, and then components, and then are assembled into full cells and welded shut here, and then brought over to Unit 7 where they undergo commercial cell testing and are ready to then assemble into a system. We also have seal assembly and fabrication on the top here, and after operation, cells are then sent to sectioning and disposal and recycling, and can go through analysis and characterization work as well. So if we start by looking behind us here, this is where it all begins, is our shipping and receiving area, which starts in the back here. You can see large storage space for our components and commercial cell components. Over here is our salt conditioning area, which is where we handle and dry our salts. It's a large paint booth used for painting large automobiles. We've repurposed it for handling our salts. Basically, when the salts, if salt dust gets into the air, it can land on steel components and cause rusting. So we want to avoid that. We also have our incoming quality inspection area here. You can see we've got some important equipment, including a coordinate measuring machine, which will evaluate dimensional specifications compared against our drawings, as well as gauges and other equipment used to evaluate the equipment. We also have some cleaning equipment here. This is an ultrasonic cleaning, aqueous cleaning system. Parts get loaded in and go through a series of cleaning stations where they're cleaned off and then rinsed and then dried and are ready for use. There's an automated lifting arm here because some of the baskets get pretty heavy that have some of the components inside that we're cleaning. All right, I'm going to transition now to another area of our lab, so see you in a moment. So So we're now at one end of the cell assembly area, and we're going to walk through this equipment behind me in just a moment. But I want to take you to the far end of our facility, which is where we do a lot of our fabrication for our commercial cells. So you can see behind me here are a number of welding stations. We have a lot of welding because we're manually assembling our cells presently. So we've got dedicated bays for different welding stations. And we'll walk through here, show you some of the other aspects of this area. So again, these are our welding bays. We've got full-time team members here that are welding components together. We also have a machine shop area behind us where we've got automated or CNC mill and lathe and other manual machining equipment, which is really important as we're prototyping parts and building components. I'm going to walk you over to this other area in our facility here. This is where we've built up and operated our prototype system, which we called our beta core unit, which is a 10-foot containerized system that was loaded with 432 of our R&D cells. And one of our goals going forward at this time is to load and operate this with hundreds of our R&D, our commercial size cells, and demonstrate that system performance. But it was quite a simple, it was a good experience in building up a system, including electronics, controls, thermal management, insulation, etc. And we're able to demonstrate self-heated operation of this unit, again with our R&D cells, and the goal will be going forward to build this up and load it up with commercial size cells and get that system operating as well. It's also worth showing you guys the inside of this container. Again, this is what we use to operate and demonstrate self-heated operation with R&D cells. So you can see here is a container that has a rack inside of it with 6 trays that can get loaded with cells. Cells are electrically isolated from each other and then linked together through series connection. And this space underneath, or the boards underneath, are thermal insulation. And then this whole cavity here is filled with patterned thermal insulation that allow the inside of this container to stay at 500 degrees Celsius, and the outside of the container is cool to the touch. Now that we've seen the cell fabrication area, I want to walk you over to the cell assembly area, which is where we load the active materials into the cell, melt the salt, and pour it into the cells. So this unit behind me is that cell assembly system. You see the 2 large blue boxes there are large furnaces, and then the metal portions or flange assemblies that you see sticking up out of the top are the salt melt vessels into which we pour the powdered salt, and then we heat that salt under vacuum, under air conditions, and melt the salt and have it ready to pour into the cells. Next we'll go take a look at how the cells are assembled on the other side of the system. So here's the front end of the cell assembly system. It's really quite a simple process. Cell components are loaded through the antechamber into this purge box system here. The calcium and antimony metals are loaded into the cells, and you can actually see some examples of cells here that have their calcium and antimony loaded into them, and the cap is welded on, which includes a pouring window. Cells are then slid over and filled with molten salt that is poured through these 2 pouring tubes here, and we're control the flow of the molten salt using a mass-based control system, and that's it. Once that's done, the cap is sealed up with an extra weld on the top, and the cells are ready to be tested. It's really a very simple and elegant process that allows us to project to be a very low-cost manufactured cell product compared to many other cell technologies. All right, and here are some of our team members that are going to be pouring some of our commercial cells. We're all ready to go. We've had the cells that are loaded with calcium and antimony, and we're going to, as the next step, we're going to pour the molten salt into the cell and then later weld it up. So let's take a closer look.
3, 2, 1. Again, 1, 2, 3, 4, go.
So that's probably the most complicated process in our cell assembly, and it's really very simple, as you just saw. The salt is poured into the cell, controlled using a mass-based control system, and the cell is now ready to be welded shut and put on test. As you can probably imagine, as we think about scaling this production equipment, our plans are to use automated robotics assembly systems to automate the pouring and welding process steps. Here's a rack of cells that we've finished assembling. And you can see the stainless steel containers, the negative terminal coming out of the seal on the top, and just for a sense of scale, these are quite large size cells, and a couple different varieties of cells because we're testing out some different internal components and dimensions as we're looking at not only the cell that for our product C, the first cell on our roadmap, but also subsequent cell products on our roadmap, and learning as quickly as we can on all these fronts. So after we assemble the cells, weld them shut, we'll do a leak check on them to make sure the welds are good. We then bring them over to do testing on the cells, specifically end-of-line testing, where we place the cell inside large heaters. Here are some examples of furnaces that we use to test cells. These are actually used for our R&D cells. But you can see here, these are commercially provided furnaces, and then you see on some of these cells, these furnaces on the bottom, you can see some current electrical leads and voltage sense leads coming out of the furnace that are then connected to big battery testers like this Ambri unit here. Again, commercially available system, which we then use to charge and discharge the batteries, measure efficiency, capacity fade, brake capabilities, things like that. And in a moment I'll show you the test furnaces that we're using for the large capacity cells, which obviously are going to be much larger. So you see behind me here is the cell assembly area and equipment in the far back, and then on the closer to me here are the R&D test channels that we looked at just a moment ago. I'm not going to walk you over to another area in our facility, which is our R&D cell testing area and fabrication location. So you can see here is where we build and assemble our R&D cells. So we've got some assembly benches here. If we walk back here, we can see one of the glove boxes that we use to actually assemble our cells. In these boxes, we'll melt our salts, load our calcium and antimony into the cells, and then pour the molten salt into the cells as well. So it's a manual process here, but it mimics the types of process that we use for the large-scale commercial cells as well. You can see behind me here is a welding station for some of the fabrication, and then another glove box here that we use for development purposes. So we just walked through the cell assembly area for our R&D cells. We're now going to walk through this other area here, which is two functions. The first one is our seal assembly area. So this is where we fabricate and build our high temperature seals, which is we use a high temperature ceramic to metal active brazing process. Cells are loaded into high temperature vacuum furnaces like the one you see behind me here, as well as the two tube furnaces in the back. And we basically load the components into these furnaces, heat them up under high vacuum, the braze melts, and then forms a bond between the ceramic components and the metal components in our seal. We also have a characterization and analysis area back here, where we have two scanning electron microscopes here, as well as optical microscopy, an XRF system as well to do elemental analysis. So basically, after we build and operate our cells and cut them open, we can take a very close look at the materials in the inside and any development and changes in their morphology for root cause analysis. So after building and operating and testing our cells, during the development process, we'll take those cells and we'll cut every single one of them in half, take photographs of it, and then ultimately dispose and recycle of the components in the cell, namely the stainless steel, for which we've got approval from the Massachusetts Department of Environmental Protection to do that process. So you see one of our team members in the back here is preparing the cell for sectioning and disposal. So lastly, I want to show you our Unit 7 space. This is a space that we use to do cell testing, both of the R&D cells and commercial cells. The space behind me here is our office space, but we'll go to the unit and next take a look at our cell testing area. So you can see here, big wide open space, and really divided into two sections. This first section here is our cell R&D testing space, where we have these large cabinets that are filled with testing furnaces, again, to test those R&D, this 4-inch by 4-inch by 2-inch cells. So you see some of the furnaces there with the electrical leads coming out that are going to battery testing systems that we have spread throughout. So you can see quite a few cabinets here laid out to allow us to have about 200 test channels operating for those R&D cells. So next I want to show you the commercial cell assembly test stations, the CETSs as we call them. These are large customized units that we've built up to test our large commercial cells. The units include a heater assembly on the bottom that has 12 insulated bays that individual cells can be loaded into. And then the battery testing systems are located on the top of those racks there. This design allowed us to shrink this overall size per channel down by about a factor of 10 compared to some of our earlier embodiments, and allow us to consume a lot less energy to keep these cells hot, because the cells that are adjacent to each other in that furnace don't lose any heat to each other when they're both operating. And that allows us to drive down the energy consumption required during this end-of-line and testing operation. Next, we'll take a closer look at these systems. So these are our commercial cell testing stands. We'll zoom in on one of these units here. You can see the commercially provided battery tester systems are located on the top of these racks, and the furnaces are located underneath. So these furnaces are hot. They're operating at anywhere between 475 Celsius and 550 degrees Celsius. And each of these bays here contains one cell. There's an insulated cap on the top. There's current leads and voltage sense lines coming out of each bay. Those current leads and voltage sense lines pass up to those battery testing systems on the very top. And so this is where we load our cells and test them and cycle them for anywhere between days, weeks, months, and years. And this design has been really helpful for us to reduce our overall footprint and energy consumption, and is the type of design that we'll use at higher volume manufacturing. We presently have 12 of these bays with 12 cells per bay, a total of 72 channels. We're looking to expand this to over 200 test channels in 2021 as part of the next round of financing. So that's the end of the tour. Really appreciate you watching and learning about what we do, and do any follow-up and any other questions you may have. Thank you for your time.